Good morning, everyone. Maybe when you arrived here this morning, got your first cup of coffee, hopefully, you explored the motor world a bit. Maybe you walked over there to the neighboring building and discovered this gigantic robot that we have there on display. This robotic arm belongs to Robotcloud. Robotcloud is a company here from Munich which specializes in building software modules for robotic arms such as the one over there. Their software enables such robots to detect objects in space, identify potential grip points, and then pick up those objects gently without squishing them too hard, obviously, move them across a collision-free trajectory through space, and finally put them down gently again without smashing them into the ground. Now, Robotcloud claims that this process is not only fully automatic, but also their setup is largely free of human involvement, or at least comparatively free compared to conventional approaches where you need multiple engineers to set up a product packaging line. They speak of a no-code setup. Second thing I found really impressive is that there's their approach is largely hardware agnostic and modular. So their customers can actually pick the robot arm of their choice. And finally, they're able to handle a wide variety of product shapes and sizes, and also weights. Now, fortunately, we have two people here today who are going to explain to us how exactly they are achieving this magnificent feat. The first of them is Ilya Dianov, the CTO and one of the founders of Robotcloud. He holds a PhD from TU Munich in robotics, and at Robotcloud he is responsible for all these interesting technical challenges such as object detection and also autonomous path planning. The second person joining me here today on the stage is Kaiser, the CMO and also one of the co-founders at Robotcloud. He has over 20 years of experience in entrepreneurship. He also holds a degree from TU Munich in mechanical engineering. And with such vast experience, he nowadays mentors people, for instance, at the Fraunhofer Institute at Fraunhofer Institute IBMT in Saarland. Now, before we start, I would like to point out that this talk is being streamed and recorded. And for those of you who are joining us today from back there, remotely, I would kindly ask you to direct any questions you might have to our Slack channel. You will find the Slack workspace we have on our website, bigtechday.com, and the room that you want to join is called Kohlebunker -2, just like the location here where this is taking place. You also find that in the program, and you also find the channel name in the first message you receive on Slack. Now, with that being said, it's great to have you here, Ilya, Thomas. The stage is all yours.
If we go through it, yeah, now it will be difficult to add anything else to our presentation because you got through it. So thank you. Yeah, we are grateful to be here and that we can show you some of our main development and, of course, achievements we got. So as Simon mentioned, we are solely focused as a SaaS solution provider for industrial robot manufacturers like Yaskawa, KUKA, Universal Robots, and so on. And this came back to, let's say, 2 years as we figured out, and we were invited to went through different kind of manufacturing areas, and we found out that mostly in any kind of end-of-line packaging, independent if it's if you're visiting maybe an automotive supplier or a manufacturer or an electronic part manufacturer, you will always find the same, nearly the same situation, where you have these monotonous work, you have very often some economically unfavorable work. Even if you find some worker, it's mostly tiring to them. And so we thought we should find a solution for that. We talked to these manufacturers and even tier 1 suppliers, whatever. And finally, we figured out that these 4 main points for them are very critical. So let's say the high cost efficiency of the installation, of course, as you probably know, having a flexible, deployable robot. You need rapid adaptation to the process environment, and of course, the robot should be operable by untrained staff. This is a more and more upcoming request. Then we saw that there was some already automated, so let's say classical automation within some of these suppliers. And I mean, these cells were designed for mainly only one application. They are very expensive and of course not very easily adaptable to a new application, and mostly without any advanced sensing. So we developed, on the base of Ilya's work at the university, the, let's say for us, more intelligent solution. This is camera-based. So we have camera-based teaching, we have independent recognition of parts and placement situations, we will show you later. And we are focused on future AI skills, so to automatically identify changes in the environmental conditions. So we see that many of these manufacturers want to move and place the platform from one place to another workstation. They have issues on, if they say, if we have different parts, if the parts is changing, they have a high variety on parts, even on boxes where they store all these parts. And they need, in that case, also adapt the robot behavior. So in terms of motion speed, let's say the end effector forces, let's say if they want to pack very densely and they want to make changes in the environment overall using this machine learning and AI. We focused that we figured out for the working process. It's mainly an issue that you have a very shortage on labor. Also, this process monotony, the type of delivery is dramatically changing. So you have unsorted parts, you have conveyor belt, you have trays where you pick these parts out, and you have, of course, changing varieties of parts. Some of these are not very easily, let's say, identified. So let's say a worker can go in and see this looks like the same, but in details they are totally different. And you have so kind of from insensitive to sensitive parts, which are very crucial if the quality on surface is highly required. So we first starting with the object to be packed. So we have an autonomous object detection. So we do this kind of Streifenprojektion and start with that. So even or independently what object we will get on a delivery by the conveyor belt, we can detect. We also have a pre-alignment of the grasp point, and then we got the object picked and forwarded to the next position. So let's say this could be also a quality station in the immediate place or even the end of packaging. And the second, after you have picked the object or the product, we are focusing on this process environment. So we saw that, or we see that in changing environments, especially if you see loose cables, you have emerging obstacles, will influence the system or the process overall. We have different workspaces, as mentioned in the beginning, and we have, of course, a high variety of parts, so different parts we can detect and we can then automatically package. So the motion sequence, we are focused in this overall process environment. We have to avoid collisions. This is something we go deeper in later, and we have to optimize the path, which is totally autonomous. And we have, of course, achieved very, let's say, important storage pattern, which we'll show later on, where we, let's say, developed some force sensing things. And we have the safety requirements from the end user, which allow, let's say, they want to have collaborative working, and they are eager to see that the overall installation should be fenceless and adaptable. So I now skip over to Ilya to go more in technical details.
So we'll talk about some challenges that we experience basically in the packaging process and that how we tackle it with our software. So basically one of the main challenges is, of course, that the installation usually have to be moved in the machine when the environment is typically unknown. So the boxes can be placed like differently, of course, like the whole setup can be placed differently. There can be like walls and obstacles around the robots. So the initial challenge that we want to solve, of course, is to actually detect and recognize like the environment and detect like where are the collisions. I mean, so typically in our case that we're showing here is the main collision here is a box. So we basically have to really detect where it is. Like we have to detect the edges that the robot has to avoid before, for example, placing the parts inside a box. So to do that, typically we really have to segment the entire environment. I mean, this is what we are currently working on. I have some example, for example, how we do it in the office. So we really have to segment the walls. We have to segment like some metal pillars which are really blocking the path of the robot when he moves. We need to detect conveyors and everything like surrounding, even the lamp, I mean, which can really influence the path of the robot. Then we really have to generate basically like a virtual representation of this environment that the robot knows when he plans where each obstacle is located and can easily navigate like the path around it. So for the motion planning, we use more advanced versions. So we don't really use too much classical algorithms, but we really use more, let's say, motion planning based on the optimization. So in our case, it's a non-convex optimization, where you can really define your problem basically as a set of constraints, can be like inequality or inequality constraints, and you really have to optimize basically your function based on the constraints that you provided. The constraints can be, for example, velocity constraints, jerk constraints, acceleration, and of course collisions as well. To really solve it, I mean, we use approach that we deconstruct this non-convex optimization by the convex subproblems, and then we basically can use a quadratic programming to solve these small convex subproblems. And the idea is to optimize basically the motion of the robot, so the motion is very smooth, and basically the robot can like easily navigate, I mean, avoiding collisions, but then still maintain like a smooth acceleration, velocity, and do not have like any jerky motion. This is basically example that we show in your office, but in reality, I mean, this installation actually runs also in production and basically doing exactly what it is, like the package, I mean, the parts coming on a conveyor belt and densely filling the box with the parts. Another basically challenge, of course, is the main details of the packaging itself. So, for example, that different types of containers that you have to handle, the different types of basically storage, and like how you really place the parts, how you orient the parts inside a box, the different requirements of how you have to handle the parts, because some parts can be fragile, you cannot just drop them in a box. You cannot like really press too much because you can just break them. So all of this has to be taken into account when you plan like the placing of the motions, when you plan basically the picking of the objects, like what orientation, like what position, how much force do I have to apply to handle the objects. So for example, in our case, I mean, we have like 2 different containers. Like one is really like one big metal box, which is typically reused by many suppliers. So it can come like in really bad condition. I mean, can be damaged, can be really rusty. So typically the workers, I mean, they are putting inside these kernel layers, which again are reused from box to box. So the quality of these layers, of course, inside can be really bad as well. So we really have to identify, okay, so how much free space we have around inside a box, how much, like how the layers are placed, so we can really avoid colliding with any of these basically layers in the box. The current boxes usually are new, so the current boxes, I mean, much easier to handle, but it has usually, of course, like different sizes, I mean, and different shapes, so we have to be able to basically automatically adapt, I mean, our paths and our placing, especially to the different types of the boxes. So this is typically what comes as a requirement, I mean, how the boxes should be filled from the customer. You can see, I mean, it's completely 2 different patterns. But the most critical part here is that we really have to fill very densely the box. We don't really have any room for error, so you cannot just drop, I mean, a couple of parts and say, okay, we're done. I mean, it's very easy. So you really have to stack the parts very close to each other. Parts cannot be damaged, I mean, and certain areas, like especially you see like this white area of the parts that cannot be touched. So the parts really have to be handled with care. To do that, basically, we have like a software which can automatically generate and adapt basically the placing pattern depending on which box it has, depending like how much free space it has, and capable of basically filling automatically any box. If the user wants, for example, change the pattern and even define like a different pattern, it can automatically infer and adapt how the motions of the robot has to be to handle basically these items and accurately place them. Another issue that we really encounter is, especially when you have such a dense filling of the boxes, that sometimes when you place, especially the last parts, they simply don't fit using conventional normal placing approach. So, for example, here you can see that since the parts are so tight, I mean, when the last part basically comes, it basically it can easily crash on the neighbor if you just try to place them like by putting it down. So in our case, I mean, what we're trying to do is we're really trying to rely on a force, because we don't simply have time to really constantly inspect the box using the cameras and the vision because of occlusions and the cycle time. So what we're doing, basically, we rely on a force, and we really try to insert the part basically inside this dense location without basically colliding with a neighbor. And this is what we did for a current project. And of course, we are working like on more advanced algorithms, how to really operate in even tighter spaces, like, and see like how similar to the humans that the robot can basically insert a part and don't damage any neighbor itself. So for the future, basically, outlook, we have that basically the idea of using AI and motion planning for such complicated challenges as packaging is very important, because typically you either have to do a huge engineering which costs a lot of money just to solve a packaging of one single part, and this is like not very cost efficient. If you want to have installation which you can easily put in any production and it can work basically as it is without any additional programming or any additional change, you really need like these advanced techniques to handle all possible challenges which occur during the packaging process. In our future work, we really want to rely more really on learning and self-learning, that the robot can basically adapt its motion based on the previous experience and can easily change from different parts to parts without completely like any additional requirements of programming, just by learning itself. Thank you for the presentation, and if you have any questions, I'm free to answer.
Hi, thanks a lot for running this presentation for us. I have just a very quick question. I wanted to ask, like, out of what we've seen, how much is like really real time in those operations, and how autonomous the machine itself is? Like, does it constantly adapt? Does the owner of the machine have like the control whether the machine, to which extent the machine should change its behavior while packing, if like it's moved or the part is different, etc.?
Typically, what is our current basically approach is that the machine is pre-set up, so it's moved to the production basically, and the customer can set it up his own case using our graphical interface. So basically, it shows, okay, so here's location where the boxes are, here's location where the parts, and set up basically the pattern, like how dense he wants to pack the parts, like what should be the orientation and position of the parts. And then the system basically is ready to go. So ideally, basically, the system can already ready for operation and operate 24/7 at the factory. During the time, I mean, we are collecting the data, but then we're using it internally, I mean, to improve and train our algorithms. But of course, during the operation, it's not really doing any improvements at the customer, because we cannot guarantee then something will not stop working, because he needs like a production which is 100% working without like any interruption. But then the data that we're collecting, we're using to improve the algorithm, and then once we really get to the stage, okay, we know that our new updates is 100% stable, then we can update the installation of the customer, but the training itself we're doing on our office, for example.
In almost all of the videos, you were using the exact same part for demonstration. Was there a specific reason why you chose that specific part, and is it supposed to simulate something?
Yeah, so for this video, we are showing the real project that we have. And the project is really to pack this type of parts basically with in production in a big automotive supplier. So that's why all the videos basically we showed exactly with this. I mean, of course, we have, let's say, other projects that we are working with other parts, and we are like still in process basically of adapting our algorithms for that. But for the videos that I have, I mean, basically all the recordings we did basically for this project. So that's why, unfortunately, all the videos were with this part.
Maybe a question from my side then. What's the biggest object you can handle, and the heaviest object, and maybe also the lightest and most fragile?
So basically, in this installation, and this robot can handle up to 20 kilos. So we obviously can handle up to 20 kilo objects. I mean, I would say like we typically can operate up to maybe object size of 1 meter, maybe by 1 meter. For the bigger objects, I mean, we then need really big industrial robots. So we typically try to employ collaborative robots, and this is the biggest one. But overall, I mean, our algorithms can handle the objects of any size, as long as it can be picked by any kind of robot, because our approach is really modular, so we really want to support different kind of hardware, and we can support big industrial robots as well. So as long as the robot can pick it, we should be able to handle it.
Can you tell us more about the setup of the robot? So what does the customer has to do when they set this up? Do they also have to, for example, have external cameras, or do you set it up, or is there a manual that they can just set it up on their own?
Yeah, so typically there are two options in our case. So if we are talking to a customer who actually has a problem with packaging, we are coming together with our partner integrator, and the partner integrator basically is building the whole installation. We are usually providing like a template and saying, okay, so this is a set of robots that we support. This is a set of cameras and set of grippers that we support. This is a like overall model, like how we typically design our installation. And then, of course, the integrator is free to choose if he follows this design or he can do some adaptations. But when you come to the end customer, basically the installation is fully delivered, is fully completely wired, and he doesn't need to do anything at all. The only thing is we need to do some connection to his machines. And typically, like the different like standard protocols, I mean, Profinet, for example, when you can connect to the machine which is producing the parts, and then it's ready to go.
I have also a question. You mentioned a little bit about further improvements and self-learning. I have a question. If you have footage of humans who do the job, do you maybe think it's also somehow possible to learn from them?
I did a lot of this work when I was doing PhD, learning from a human demonstration. It's always a problem that you really have to do a correct demonstration because you're learning as good as your demonstration is. So if the worker, for example, is not really experienced how to train the robot and how to do these demonstrations, I mean, in this case, it creates even more complexity because, first of all, you really have to correctly identify his motions. You really have to basically segment and see how he manipulates, I mean, how he interacts with environments and so on. But then he has to show exactly the correct version because if he shows something which the robot, for example, cannot feasibly do because he, first of all, has only one arm and the human has two, so in this case, I mean, it will only create issues. So for now, we are not looking into this. In the future, I mean, we considering looking into, but typically still trainings and by the experts, for example, us, who knows how to really do it correctly.
Okay, thank you very much.
Sure.
So in the intro video, you showed like humans placing some stuff into a box. And do you also have experience with like picking soft objects, like the plastic bag that you showed or something like that?
Yes, we currently actually have a project ongoing to pick basically a plastic or a plastic bag filled with the parts. So this is what we're currently looking into. I mean, I don't unfortunately have any videos to share, but of course it, let's say, even creates even more complexity that how you handle this deformed bags. I mean, how can you really hold it without like dropping it, for example, and how to insert it inside like a small box which doesn't have much flexibility. But this is what we are currently looking into as well.
Thank you.
So what are the constraints in terms of the location you set it up? So if I understood correctly, you mainly use cameras as sensors. So do you require like constant lighting conditions that don't change, or is that no constraint at all for you?
It depends on the type of camera you can use. If you use, for example, if you have conditions when the light is always changing, you can use time-of-flight cameras, which obviously are more robust to that. If the conditions, for example, of the light are less influential, I mean, we have some different cameras like Zivit, for example, which doing a pattern projection, which already can handle different light variations. And definitely, I mean, the camera configuration for the custom, I mean, setup is a challenge, for sure. And I mean, now, of course, we are doing it ourselves. I mean, in the future, I mean, would be nice, let's say, if there are some automatic methods, I mean, but we are not really working on this direction. So we are basically, if there will be someone who supplies, I mean, these methods, we can use it. But there are, let's say, options, I mean, how to handle this different illumination at the customer.
Thank you.
I think it's interesting that you can deal different kinds of robots. I can imagine that several robots have like different interfaces, like commanding position of the robots. Maybe one type of robot has it, and another type of robot is able to command forces or torques. So how do we deal with different capabilities of the interfaces to the robots?
Yeah, so we are trying to develop our software more modular. So we're using this ROS2 as a main kind of like framework to communicate between different nodes. And since it allows us to kind of build our control nodes more like a robot agnostic, so you just have to basically take care of this on the robot driver side, which interfaces it allows you to control, like position interface, velocity interface, torque interface. Typically, I mean, majority of the robots, industrial robots, I mean, they don't have any torque control at all. So they usually have a position control. Some has velocity control as well. Of course, I mean, depending on which type of the robot you have, I mean, you would have to basically expose the case of which control interfaces are let's say, available. And based on this, I mean, the software can basically select which controller it uses, I mean, to basically move the robot, like position, velocity, and so on. And like, since it's modular, you can plug different robots as long as you provide basically a kinematics model, as long as you provide basically the driver. Then the motion planner, for example, can still send the same trajectory on this robot, and it will move in a way that similar to the previous, basically, robots that we used before.
And do you have limitations on your capabilities as a robot doesn't have torques?
Yeah, it depends basically on which features we use. Of course, I mean, if the robot, for example, does not even allow you to command position or velocity at all, then we can say, okay, we cannot at least use any force control, like we cannot do anything with the force function, because you just have to, I don't know, execute only trajectory-based, right? So when you cannot even control when the robot basically moves trajectory, like if you have to adapt it. If you say, okay, I mean, you have some position control, but not velocity control, then we have some as well limitations on the features that we can do with the current installation. But we typically trying to, of course, select the robot which, let's say, more suitable for the current, let's say, project, right? We're saying, okay, if we have a specific packaging process in mind, we usually say, okay, we recommend this and this robot because it has like this and this interface, and we basically see it more compatible with this packaging problem.
Thank you.
There is also a question in Slack from Marco, who is asking, do you use any kind of digital twin when adapting the machine behavior?
Yeah, we have a digital representation of the whole environment, where basically the robot and all the obstacles that we detect, I mean, updated in the real time. And this environment is used basically for planning. It's not a one-to-one digital twin, so many, like say, obstacles are simplified, because if you really have it as a complex CID, then collision checking just takes a very long time. So we're trying to simplify basically the environment as much as we can to speed up the collision checking. But the environment basically is still a representation of what we see like around the robot.
All right, thank you. And then there's another question from Kilian, who is joining us from Australia. And he's asking about the machine learning part. I guess the question is, how many different models do you use in the overall ensemble for the robot? And if you can talk a little bit about the data collection that you're using, and do you do manual labeling, or is it a lot of unsupervised learning in there?
So for now, yes, we are doing some supervised learning. So in our case, like is force basically feedback when we inserting the objects, for example. I cannot talk about too much in details in the models that we use because it's proprietary information, but I can say that basically the training now we are doing like in-house, so we are basically developing all the training like in-house. We are doing, of course, the labeling for the different packaging problems that we encounter. In the future, I mean, we really try to, of course, to incorporate as well the training, like when the robot is operating at the customer, I mean, to collect this data and incorporate in the training, but this is more future work for us. Basically, I don't know if it really answers, I mean, the question, but I cannot talk too much into detail because this is still our, let's say, proprietary technology that we use, and we cannot really say too much about it at this stage, at least.
I would like to ask about speed and performance. Time is money. How fast do you think you can get with this system, and what's the limiting factor? Is it the AI detection part, or the movements of the robot, or the optimization movement problem?
It actually more depends on really the speed of the robot itself. So since we are using collaborative robots, I mean, depending on safety situation as a customer, you have a maximum speed that the robot in general is allowed to move. So typically, the current robot that we have can support up to 1.2 meter per second, the movement of the end effector, of course. But in case, let's say, when the human is entering like really the safety zone, usually the speed is like around 600 millimeters per second. And this will be your limiting actually factor of the cycle time of the robot. So our software basically is trying to always comply. So we always try to do the planning in parallel. So we don't waste time, I mean, to pre-plan each motion basically. And the robot moves as soon as current motion is finished, he moves to the next motion. We as well working on optimization of the vision part. So we basically trying to really have a detection sub 1 second, basically. So up to 1 second, I mean, typically the detection part takes place. And the scan is, I mean, is not constant, right? So we're not constantly scanning the environment, but we're doing the initial scans, and we basically start the process to save the time. So mostly, I mean, your speed is influenced by the robot. If you use industrial robots, they are much faster, and you can, of course, move much faster, basically. But in the current, like especially collaborative installations, I mean, really is a collaborative speed which is a limit.
All right, and other question from Australia. The question, sorry, just waiting for the siren. All right, the question is how many jobs will basically be replaced by the robot in a factory? And I guess when do you reach, or when does the factory owner reach a positive return on investment?
So in the current project, basically, we have already that the customer is already reaching a profit of investment because he's saving approximately 1,000 euros per week. In the current project, there is a 3-shift production. So we are saving approximately how many?
I mean, mentioned that we save the customer 1,000 euros per week, and he has a 3-shift thing, then it's 3,000 per week, yes, and that's the actual case. And if you compare to the, let's say, original or the normal kind of programming, it will be probably 60% higher than ours. So as our model is, so we have the modularized kind of SaaS licensing, then comparison is probably 20,000 euros for 3 years, roughly. And if you save it like these customers, so let's say 3-shift, then 3,000 it can count up.
How do you manage the unpredictability of AI in contrast to the safety constraints?
So the safety is set up completely separate from our system, basically. So we have, first of all, internal safety on the robot controller itself, which you can set up basically at different security zones. We have a laser scanners, which basically are scanning like when the human is approaching and detecting like on to which distance each person is coming. And we have different security zones. For example, say, okay, so when your zone is when the system can work as it is, there is no people around. Then basically when he steps in, the robot slows down. And this security is basically controlled by the robot controller. And it overrides basically whatever we commands that we are sending with our software. And then it kind of ensures the safety because in this case, I mean, if our software for whatever reason can send some crazy speed or crazy position, the internal safety basically unit is overriding it and saying, okay, it's not allowed to go there, or slow down, don't go so fast.
Okay, I have so many questions actually still, but maybe the first one would be, you mentioned that you're scanning the environment about once per second. Is latency and is performance any issue for your software? Is that the reason why you picked only 1 frame per second, so to speak, or could you also speed this up, or is this not necessary?
No, we are not scanning one per second. So the detection part, at least when it comes to the part detection, we are trying to do the algorithm takes less than 1 second to do the actual estimations. But the scanning itself, I mean, the scanning of the process, especially of the entire environment, of course, it takes much longer. But this is a kind of initial setup. So what you basically have is, and when you move the installation to the customer, the robot scans the environment, so he takes some preparation step. And that step can, of course, take, some minutes even. But once, he's done, he's then ready to go. And then, the only thing he's scanning is, and when the new boxes are coming, he scans the box position. And then, we typically using, let's say, this cameras with a high resolution. But you can have, for example, like a 10 gigabit LAN card, which can speed up like the data acquisition. And the algorithm itself, we are trying to, of course, to optimize again to process it up like 1 sub-second. And then you scan the parts as well, which we basically, again, optimize, to have it faster based on the latency and fast on the processing. But you do not scan the entire environment because this, of course, takes much longer.
Thank you. Well, if no one else has a question, I have another one, the final one. So you mentioned that you're actually only producing the software, right? You're offering software as a service. You're not producing the hardware yourself, which I found really interesting because I once tried to, or a few colleagues and I tried to build a object recognition platform which consists of both software and hardware. And our biggest challenge was that installing the hardware, buying the hardware, maintaining it, would have just driven the costs up far too high. And I'm wondering, so since you've already worked around this issue basically by just producing the software, what has been the biggest challenge for you from a business perspective?
The biggest challenge is probably, we are focused, or let's say our customers are the hardware manufacturer, like for saying Yaskawa or Kuka, whatever, and they buy our solution, so on a license model, and instead of doing their own programming, they use our, let's say, pre-programmed solutions on an app base, similar, and so the hurdle is to, let's say, convince the hardware manufacturers that it's very easy to adapt, to integrate into their process. Yeah? So, but we see extremely, would say, acceleration in that process, yeah, because as we see, that's the feedback over, let's say, 2 years, that the hardware manufacturers mainly focusing on hardware. The components manufacturer on components, they try to do some singular software solutions, but overall for the process, and the process is diverting into many fields, many niches, it's very attractive to them to use that kind of Robotcloud offering. Yeah.
Thank you. Maybe actually one more final question. Are you profitable yet?
No, we are not profitable yet, but we are focused being that in the next 2 years. So we have a bunch of current projects, and we have a lack of, let's say, getting people, of course, IT specialists with some experiences on autonomous things around. But we are hard working on that. But we do not have any VC money in so far. Yeah, that's also interesting. So they started with an early, let's say, money we spent by ourselves. So let's see.
Well, I wish you the best of luck. And unless anyone has any questions anymore, then let's please give it up for Robotcloud.